Okay. Hello, everyone. Welcome to the verification seminar, IARCS verification seminar. It's a pleasure to have Thejaswini with us. Thejaswini is a postdoctoral researcher at IST Austria. She did her PhD at Warwick with Marcin Judzinski. She works on games and several other things. So she's also a previous student of CMI. Looking forward to your talk, Thejaswini. Over to you.
Thank you very much for the invite, and uh, I'm very happy to be talking here. So today, as we heard, we'll be talking about games in general. So the title of the talk is Rabin Games in Colourful Trees, and a paper under this name was written with Irmak Salam and Rupak Majumdar. But then I kept the same title, and I thought I would also add some other results of ours, which kind of elaborated on these what we obtained over here. So you can think of one of our half of the talk as like an upper bound or for Rabin games, and the other half as some kind of lower bound result. And before I start, I just want to say feel free to unmute yourself and speak if you have any questions, or stop me if something's unclear. So today's talk is going to be a bit combinatorial and math heavy, but maybe I will start off with why we care about Rabin games. I'm sure this audience don't need no actual introduction to it, but I mean, it's a verification community, and what we usually want to do in verification is you want to check if some machine which probably interacts with some kind of user regularly does the things that it's supposed to do. But what these games are motivated by is more, let me say, reactive synthesis. So here again, you have this machine that you want to synthesize, and you know that this machine interacts with some kind of user. And like you are given some kind of specification that you want this machine to satisfy. It could be something like LTL or CTL. So what usually you do is take these LTL formulas and then convert them into some kind of an automata, non-deterministic Bucci automata, let us say. And then for non-determinism is not very good for us. So you determinize these automata to either get a Rabin automata or a parity automata. We'll see what these are and what a Rabin automata at least would be. And what we have is a deterministic Rabin automata. And now you want to synthesize a machine that interacts with the user such that no matter what the user says, you want it to satisfy this condition that this deterministic Rabin automata says it should satisfy. So what happens when you have this kind of setting is Rabin games. So this is the very short introduction to why we care about Rabin games. From henceforth, we will only care about, look at it as a mathematical object in some sense. So what are Rabin games? Rabin games are two-player games played on a graph. And I will try to call these players Adam and Eve, but if I slip up, please point this out, I might. So there are two players, Adam and Eve, and Adam I will denote with a triangle whenever I can, and Eve would be the square player. And there is for Rabin games, I will say that a Rabin game has some finite set of colors. So here, if you can look at these colors, they're blue, purple, and green. And other than this, each state has this color occurring either as a smiley face or a sad face, or it doesn't occur. So if you look at, for instance, this, let me try to, if you look at this state here, then what it does is it has the purple face occurring as a smiley face, and then this state over here has a green face occurring as a smiley face, but the purple face is a sad face. So we are in this, what is a Rabin game? It's played by moving tokens along the edges of a game graph. So what we do here is, let's say there is a token at this vertex. And how is this game played? This token is moved along an edge, and by whom? Well, whoever owns this vertex. So here, the token is placed on Eve's vertex. So she chooses which of the next two states that she should go to. And let's say she chooses to go to this state to the right, and the token also moves there. If you look at the bottom, this kind of records the events that happens. So here in the first step, we saw that it was in the square, like in the previous, in the previous step, the token was in a state which has green as a smiley face and purple as the sad face. So that's recorded. And when the token moved, whatever place the token visits, we kind of record the faces that occur over there, the sad or the smiley face. And usually this game, now let's say this game goes on forever. So what do you have? You have some kind of an infinite play, and in the end, I'm going to assume that it's stuck in this loop, which is highlighted over there. And when do we say that this player wins a play? So Eve wins a play if the following happens. So we will talk about Eve only now. So this play we say is accepting for Eve if there is some color. So in this case, this color is going to be green. So there is some color such that after some finite amount of time, this color only occurs as a smiling face and never as a sad face. So in this example, if you see here, for green, after this point of time indicated by this green arrow there, she is only seeing green as smiley faces. The same is not true for purple. Purple, forever you keep seeing both sad and smiley faces. Whereas for green, after this point of time, you're only seeing smiley faces. So let's take another example. Instead of being stuck in that loop, if Eve decided to go go right, then left, but then she's stuck in this loop of the right to left, this loop that's highlighted here, you can see that it doesn't satisfy the Rabin condition, winning condition for her. Why is that so? Because there is no color, both the colors that she's seeing, green and purple, for neither of them. There is no finite time after which only smiley faces are being seen. If you take green, it sees both sad and smiley faces forever. If you look at purple, you see sad faces forever, like because this vertex is got this sad face. So this run would be rejecting for Eve. It is well known that Rabin games, if you give me a game graph and you tell me what the colors are and which ones are sad and smiley faces, then there is a positional strategy for Eve. So she can always, if she can win at all, then she can always win by only taking like some same edge at every step. So in this very specific game, if you stare at this for very long, you'll realize that the highlighted edge, if she takes, then she can always win. In other places, she doesn't really have a choice. So if she takes this edge, then all infinite paths in this graph satisfy this condition for Eve. So is this fine so far?
Yes, yes.
Yeah, okay. So this is what this is a result by Emerson and Jutla, and it was proved like in 1988 that Rabin games have a positional strategy for Eve. And not just that, it's NP complete. So if you have a Rabin game, you of course can give me a strategy, and in polynomial time, you can verify if this strategy for Eve is right. But you can also prove that it is NP hard to come up with a strategy for Eve. So Rabin games are known to be NP complete. So let's look at some kind of history on still like people trying to optimize these the running time for these games. So as I said, Emerson and Jutla came up with the first like algorithm that took nk to the 3k time to solve Rabin games, and then it was Newell and Rosner gave like a similar another algorithm of a comparable running time. Then if you look at this, okay, maybe I should tell you what n and k are. N here denotes the number of vertices in the Rabin game, and k is the number of colors. So we will use this notation throughout. There are n vertices in a Rabin game, k colors. So what I want to highlight is that there has been a lot of work done on this after, the very first algorithm. And all of these kind of improve the running time based on K. So if you look at this, you have all these algorithms that take, and if you look at the dependency on the first two algorithms, it had a K to the 3K and N to the 3K rather algorithm. And then you later on see that Kupferman and Bari reduced it to MN2 to the K factorial. And Peterman and Neely's paper also gave an algorithm which was like n to the k instead of n to the 2k times k factorial. But I mean, there are some star asterisks that I put there, but that's to kind of indicate that whenever someone comes up with a faster algorithm for parity game, you involuntarily sometimes also make Rabin games faster because you can convert a Rabin game to a parity game and then solve the resultant parity game. But let's not go into that. Let's then see what happened. The next major breakthrough for solving Rabin games came in 2017 when Kalud et al. In their stock paper gave this algorithm to solve parity games, but they also discussed Rabin games at in like one section of their paper. And they said, okay, really what you can do is Rabin games, this is what I mentioned before, using very well-known constructions like Safra's and Harrington. So anyway, their constructions, you can construct, given a Rabin game, a much larger parity game. It contains like k factorial times n many vertices and 2k many priorities. And from such a parity game, if you later apply their algorithm that they came up with in their paper, or any of the other algorithms that now solve parity games in quasi-polynomial time and also fixed parameter tractable time. So then what happens is you can in fact solve Rabin games in what is known as fixed parameter tractable time, which kind of essentially just means that you have this k, the function of k kind of separated out instead of being in the exponent of the n. Usually there was some n to the some constant times k dependency, but now you don't have this and you have a poly in n times k factorial to the O of 1 time. And this was their breakthrough result, which also, I mean, they also showed that parity games can be solved in poly in n times some function of k, and this kind of already gave this fixed parameter tractability algorithm for Rabin games. But I want to indicate one thing that happened here is that if you look at this construction of theirs, it expects us to construct the whole parity game when you want to solve a Rabin game. This means the algorithm would take exponential space in terms of k, because you have to like kind of keep track of all of these k factorial many vertices at least that you would construct. And even if you use more space efficient parity game algorithms, the amount of space that you would require to solve these games turn out to be exponential in k, and this is something ideally that we would like to avoid. So what like if you want to tune out at the talk at this point of time, the TLDR version is that we come up with an algorithm that actually solves Rabin games in polynomial space and also reduces this running time, like removes the dependence on k, improves the dependence on k factorial. And this is the first part of the talk that we will be talking about. And maybe for some time I will explain to you how we do it, but at a relatively high level. We won't go into too many details. So for this, maybe I will tell you not the algorithm itself, but just some kind of like an idea on why we could, like the idea behind this. Of course, there was something about colorful trees, and I want to make you look at why Rabin games can have these colorful trees embedded in them. So let's just say you have a Rabin game, and this is this big box that I have indicated here. And what is this Rabin game? One property of this Rabin game, which I promised you, is that in this Rabin game, there are no blue sad faces. The whole game has only, if at all some vertex has this blue color, then it's colored with a blue smiley face. Right? And I also tell you that actually Eve can win in this game fully, and she has a winning strategy. So let's say she fixes this winning strategy. She only takes this winning strategy at every vertex. So you can really think of it as a graph rather than a game, because Eve will only do her fixed set of strategy edges. So this is kind of like a Rabin graph where all infinite paths are winning. right? So you have a Rabin game. If Eve always decides to do the same thing over and over again, it's a one-player game in some sense. And since I promised to you that this is a winning game for Eve, then all paths, no matter what Adam does, this infinite path that is formed in this graph that is obtained is winning. And what can happen if someone promised me that any path that starts which does not have a blue smiley face has this property that in some finitely many steps I can visit some blue smiley face, and this is true for all vertices that don't have a color blue. If they can visit this blue smiley face, then then this game has a very simple winning structure, because no matter where you start, you'll always win because you will always see a blue smiley face forever, and this satisfies the Rabin condition. If not, then what we say is that, I'm going to go over this quite quickly, is the following. Sorry, this doesn't move. Is the following. So if this doesn't happen, then we argue that you can kind of recursively decompose this game using some strongly connected components, such that if I'm just going through this quickly, so because I realize that it might be a bit. If you can recursively decompose this game into strongly connected components, such that if you stare hard at it, then you would, this kind of looks like a colorful tree. What I will do is, maybe I will not go into the exact details of this part of the talk, but I will be very happy to explain it to you because I have the slides. Then we can come back to it in the end if you are still interested. So what happens is, when you have a Rabin game, and if it is winning, there is some kind of a colorful tree hidden in it. And maybe we will see what exactly a colorful tree is, and do more combinatorial stuff using that, and then maybe come back to this. What is a colorful tree? It is an ordered tree. Ordered tree kind of means that the orientation of the tree matters. The fact that the first child of this tree has 2 leaves and the second child has 4 leaves is important to us. And if it was the other way around, these 2 trees wouldn't be considered the same. So colorful tree is an ordered tree. But not only that, it has its nodes colored from some set of colors. Right? So it has some finite set of colors, and each node has some color with this set. But it has more specific than that. What we say is that we also require it to have some kind of distinct colors from root to leaf. So if you look at this example and you go from the root to the leaf of any of these paths, then all the colors that occur here are distinct. So if you look at this is black, and then, oh, sorry, I can't point here. So this is black, and then this is blue, and then you don't see blue occurring anywhere in its children. So if you have these colors, then you end up only using them only once in any root to the leaf. What does this also do? This kind of bounds the height of the tree by at most this size of the number of colors C. So if you have like 5 colors, then your height of the tree can't be more than 5 because you'd run out of colors quickly. So this is what a colored tree is, or a colorful tree is. And as I mentioned before, the fact that it is ordered makes this tree, which is the mirror image of the other, not equal. So if the order in which the children occur and the color occurs matter. Even if it's the same color, these two are not equal. And can someone tell me why? This is like spot the difference, right? These
Bottom
two.
left has
Yeah.
red children and blue children.
Thank you. So that's exactly what I was looking for. And the bottom left colors are different over here. So they're not the same trees. And I say one tree can be embedded inside another colorful tree if the following is true. Well, I wouldn't define it, but I'll tell you by examples. So this tree can be embedded in this tree because I can kind of give a map which is order preserving with respect to this thing, where the root can be mapped to the root. They're the same color. And then this first green child can be mapped to the second child here, which is also green. And the second child, which is purple of this tree, maybe I will highlight this here. So this can go map itself to here, and this goes maps itself to there. And similarly, this goes and maps itself to the child there, and so on. So this is what I would say it can be embedded, because you can kind of delete some vertices, which are highlighted here, to obtain this tree in some sense. The embedding is child preserving. Yes, so you kind of need, if like I embed one node, if I map one node to a node, then its child should also be mapped to the child of that node. So you, I get, yeah, thank you. So this is what I mean when I say a tree can be embedded. Similarly, this tree can be embedded into that. And I'm sure you can all come up with a map to do this. So you kind of just drop the middle thing and you obtain back the tree. So that's one way to think of an embedding here. But maybe this is an example of what cannot be embedded. This tree can't be embedded into this tree, because if you map this green child over here into this, then there is no purple node, which is a child of this green child. So you can't embed this tree into that tree. Now, another example is this, which is a positive example of embedding, which is this tree can be embedded into this very large tree. And if you stare at it long enough, I'm sure you'll find an embedding, but there's so many of them that you can just find there are in fact many embeddings, but we don't care about that. And why is this true? And why could I look at it and say, oh, this will embed this? Well, this exact tree that was shown in the previous slide and is here is what we also called a colorful universal tree. A tree is said to be a universal tree, or rather, it's said to be n universal for a fixed set of colors C, if no matter which tree you give me, which uses these C colors and has at most n leaves, I can embed this tree into this tree. So it's large enough that it can accommodate any tree with n leaves and the colors from this fixed set of colors and a fixed root color that can sit comfortably in this. So, okay, now maybe we have some time. So it's fun to do an exercise. Can someone like construct a very naive universal tree if I fix N and C and everything? Okay, one naive way I will start is this following. If I have some finite set of colors and I have a fixed N, there are only finitely many trees that you can form, which are ordered and uses these set of colors and has only N leaves. I say finite, it's finite with respect to N and the set of colors and so on. So since there are only finitely many trees, you can kind of put them all together, one after the other. And definitely this tree would be large enough and you would always find one of these trees embedded in it. So that is a possible universal tree. But maybe something more clever would be something like this. Someone fixes this root color to be blue and then says the other colors are these three colors, yellow, red, and green. Then what I can do is the following. I can say, okay, so I will take the root color as blue. I will make this, sorry. So at this root, I have maybe no matter what tree it is, it can't branch more than n times, right? Which I need to embed into this because it has at most n children. So I will repeat this pattern of yellow, red, green, n many times in the first level. So this will happen once, this is the second time it happens, and it happens n many times, let's say. And then for this node, let's say, for this node in the tree, I further do this again n many times. But this time its children would have the pattern red, green, and that happens only n times. So this happens 1, 2, and n many times. And then this further would branch and n many times, but this time it will only have the color green. Maybe this is not a good indicator of the color green. Yeah, it will only have the color green, but that will happen n many times. Is this clear? So this, I claim, would be a universal tree. And what is the size approximately of this tree?
So by universal, you mean that any colorful tree embeds into this?
Yeah, any colorful tree which has size at most n, or which has at most n
Okay.
leaves.
At most n leaves. Okay.
At most n leaves. So first, maybe we will see why this is universal. Because let's take any tree which has root color is fixed. So you have this fixed root color, which is blue. So the root color is going to be the same blue for all the trees that I want to embed in it. And then after that, let's say this tree has some kind of some number of children. At most, it can have n children, right? Because it has at most n leaves totally. So it can have some number of children, which is strictly less than n. No matter what the colors of these children are, I should be able to find a way to embed them in there. Let me take yellow maybe here. Let's say this is the 3 children. Then I should be able to embed this into this because the root will go map itself there. And the first child will go map itself in this green. The second red will map itself here, and so on. And is this fine?
Yes.
Yeah, okay. So like what we have is this kind of construction. What it does is at the root, it starts off and then it branches into n times, maybe yellow is not the right color. It branches into n times k in the first step, which in turn branches into n times k minus 1, and that in turn branches into n times k minus 2, and so on. And this has essentially size n to the k times k factorial. Right?
Sorry, but what if the root of that tree you're trying to embed was not blue?
So we are only assuming the property that the color root of the tree is always blue. So this is one thing that we have fixed.
Okay, fixed root
We
color,
can we assume that the root color alone is fixed, but everything else we don't know.
Okay.
So yeah, we assume that the root color is fixed and the set of colors are also fixed, this set of colors which is C. And we also know that it has n leaves. This tree that we are trying to embed has at most n leaves. And we want to find the size of this universal tree. And one construction where we go from the root and then we just say, okay, I'll just alternate. If my colors are yellow, red, and green, I will do yellow, red, green, but n many times at each level, essentially. Whichever colors I have remaining, I will just keep alternating it n times. Right? So if we do this, the size of the tree turns out to be n to the k times k factorial. And if you look at this, this is very eerily close to the algorithm of Peterman and Muley in their 2005 paper. And we argue that essentially what they do is some kind of construct this kind of universal tree underlying in their algorithm. And now,
Excuse
if
me.
you...
This would
Sorry?
be the number of leaves in the tree, right?
Yes. This is the number of leaves in the tree, and but the number of nodes in the tree is not going to be more than n times this. So a polynomial times this factor.
Okay.
So it's not too different. So, we will ignore polynomial factors now because we are dealing with so many exponential systems that, another n is not going to add too much to our counting. Okay, so this is one universal tree. And what we did was we used techniques from these universal tree literature that already exists for parity games and kind of came up with this other universal tree, which does the following. It's a recursive construction, and I will try to explain it as quickly as I can. But so you have at most n leaves, right? So if you have any tree, we just want one observation. If you have any tree with at most n leaves, you look at the root, it has at most one child whose subtree has more than n half many leaves. All of its children, if it has more than one. So let's say I have a tree And let's just say these are all subtrees, and let's count the number of leaves in this subtree. And I'm just saying something very simple. I'm just saying 2 of its children can't have more than n half many leaves. This is just absurd, because if you totally have n leaves, then you can't have 2 children that have more than n half many leaves. So what you can do essentially is say, okay, if someone inductively told me how to construct a universal tree that in fact had, think of it as a black box algorithm, I give you N, I give you C, and it constructs me the universal tree. And what I will do is I give this black box algorithm N half and then C, and it constructs me some universal tree with the root color blue. So this algorithm also takes into account what the root color is. And this will be a universal tree that it constructs. And I take 2 copies of this universal tree, and then I plug it on either side. And then what I do, I use this black box algorithm again and ask it for an inductive construction of universal tree, but this time with N and C minus the red color. Sorry, yellow color rather. And then I will ask it for C minus the red color and then C minus the green color. Let me write this here. And with yellow here as the root and red here as the root and green here as the root. So what I'm doing is, with this observation that not too many of the children can have n many leaves in the subtree, I say, okay, there should at most one of its children have n half or more leaves in the subtree, and I can embed that into one of its over here or here or here. And then the rest I can embed comfortably into this because they all have less than n half many children. Because this tree, by induction, is n half universal. So it can embed any subtree, any tree, but with at most n half many leaves. So this kind of like inductive construction, then you can do some kind of recurrence and solve this. And what you get is kind of that these trees that you can construct inductively have size k factorial, or mod c as I've written here, factorial to the power 1 plus, this epsilon is a bit too much. It actually is 1 plus little o of n1. So it vanishes as the number of as your value increases, this actually becomes smaller than any epsilon. But this epsilon is an over approximation to the size of these trees. So the size of this is mod c factorial to the 1 plus epsilon times polynomial in n. And like using this kind of construction, what we could do is just somehow plug this into a very, you can solve Rabin games using this tree almost, and then very little machinery on top to in fact solve these games, and also time k factorial to the 1 plus, as I said, little o of n rather than epsilon, and some product of some small polynomial. So this n square is time would be the time taken, and the amount of space that is required is actually quite surprising. It's very small. It's in fact just n. It's like nk with some logarithmic factors. So this is pretty much linear, especially in cases that happen in real life. K is very small. So you can think of this as just linear in n amount of space that is required. And this comes by essentially succinctly encoding these trees and storing them in like a short way. So this pretty much puts our algorithm. Yes.
Where does this n colorful trees fit in solving the Rabin game?
Yes. So this is something I went through too quickly, I suppose, which is that if you take a Rabin game in which all paths are winning, you can kind of successively decompose this algorithm Think of it as some kind of SEC decomposition, but like each SEC has a specific color, which kind of tells you what color Eve can use to win in that SEC, or which is the best color for her in some sense. And this kind of structure of the winning sets of a Rabin game leads to some kind of a colorful tree. And what we are doing is essentially searching for this tree in the universal tree set for a Rabin game. So each Rabin game, yeah.
So when you say all paths are winning, is that true for the full game, or is it only for that top layer of?
So this is true for the whole game. All infinite paths are winning for this game.
But then what is, I mean, isn't that a trivial winning strategy? I mean, Eve can just play anything, right?
Yes. So like what we are saying is, if Eve has a winning strategy, then the game looks like, it can be decomposed to look like a tree. So then you take a universal tree. Okay, so if Eve has a winning strategy, then the game looks like a tree. So
no,
if
I mean,
all...
if all infinite paths are winning, then what am I missing? I mean, does
so if Eve has a winning strategy, then we take that strategy, and then all infinite paths are winning. And then the game has the shape of a tree.
Okay, so you prune the game based on her strategy, and then look at
yeah. So in some
paths.
sense, what we are doing is, instead of looking at all possible strategies for Eve, we are looking at all possible tree structures that can occur due to a strategy of Eve.
Due to a winning strategy.
Yeah, due to a fixed winning strategy. And if you cannot find such a tree inside this very large tree, then you can conclude that Eve has no winning strategy. So you just need to look at this search space, which has this size, which is k factorial and polynomial. I mean, this is also not very hard, but I guess it's not, can't be done in 20 minutes, or like can't be done in a short talk. But it's kind of easy enough to see that, like, if you stare at it for 1 hour, I'm sure like everyone will come up with on how this tree happens in this game. And it's very basic. Like, you can just decompose this game into SECs and use the fact that all paths are winning. And you kind of like can extract a tree from this winning structure. Okay, so now we have this very nice algorithm that solves Rabin games, and it's based on this very nice combinatorial structure of universal trees. So then one can ask, can you build better trees? Can you make them smaller? Can you make this algorithm do better? We learned that like combinatorially, this is like up to a polynomial factor, very tight in terms of construction of these trees. So you can't do at least better by constructing trees. So this leads us to the second part of the talk, which is, can we do better at all, like some other way? And well, it was already known, well, maybe I'll come to that later, but we know that NP hardness of Rabin games already tells you that unless you believe P equals NP, there will be no polynomial time algorithm to solve Rabin games. This much we will all probably believe. But what do we, like, no polynomial time and k factorial to the times polynomial in n, there's a large difference between this. And if you just assume P not equals NP, you can't prove like stronger assumptions than, oh, there is no polynomial time algorithm. So what one can do is strengthen this hypothesis. So instead of saying unless P equals NP, we can strengthen this hypothesis to something like the ETH, which just says that SAT will have no sub-exponential algorithms. So you can, like, SAT can't be solved in, I don't know, quasi-polynomial time, or like n to the 2 to the square root of n time, let us say. And this is what the exponential time hypothesis says. Assuming the exponential time hypothesis, you can easily derive P not equals NP, because it's like a stronger version of P not equals NP, right? And under this assumption, what, again, the TLDR and the summary for the rest of the talk is that you can actually prove some kind of tightness of our algorithm and say you can't do better. So it's already done by Kalur et al., this exact tightness value. But then our proof the one I will be showing here is a proof that we came up with, and this was published in SOSA. And I believe this is at least simpler than the one that was done by Kalur et al. Before. So what we did was introduce this problem called permutation set, which we believe is also a very cute problem. So what is permutation set? So you have k temporal variables, let's say some x1 to xk. And don't think of this as variables which takes true or false values. They don't. They kind of need to be permuted. So you can think of them as existing on some number line, and you want to see like which order these x1 to xk's occur in. But what our actual literals will be is of the form of comparisons. I'll call them comparisons because it makes it easier. So all our literals in the SAT formula will be of the form xi less than xj and so on. And what our clauses will be like will be an OR of these comparisons. And sorry, I think I wrote conjunctions, but yeah. And then permutation set would be an AND of OR of these x1, clauses of this type above. So maybe I will show you this example where you take a clause of this form, clauses of this form, and you have like an AND of these clauses. And I say that this permutation satisfies this clause, set of clauses. So why does this do that? Like if you look at the first clause, it satisfies x3 strictly less than x1 here. So you can see that in fact, x3 is less than x1 in this permutation. Then here you also see that x4 is strictly less than x2, and then x3 is strictly less than x6. So this SAT formula, or permutation SAT formula, is satisfied because there is some permutation written above which actually satisfies this formula. And one thing we showed in our paper was that, in fact, this kind of permutation SAT cannot have a 2 to the, there is no 2 to the little o of k log k algorithm for permutation SAT. So what is k log k? Like, in fact, the reason we write k log k here is that k factorial, which kept coming in our algorithm, is 2 to the big O of k log k. It's because we know that k factorial is contained within this k by 2. So we know that if this permutation SAT problem can't be solved faster than 2 to the little, there is no 2 to the little of k log k algorithm to solve permutation SAT. And essentially, once you have this, what we do is kind of reduce an instance of permutation SAT to a Rabin game as follows. I can even do the reduction. It's very simple. So you can think of this as following. You have an instance of permutation SAT. Adam essentially says, oh, you have M clauses. Try to satisfy one of these M clauses. So the game goes like this. I'm constructing a Rabin game. So Adam at each step would say, okay, this time try to satisfy C2 for me or something like this. And then what Eve will do is she has an option of saying, okay, C2 is satisfied by some literal, like some comparison that occurs in her clause, right? And the way she does it is she has access to this grid of vertices, all of which belong to, you can even assume it belongs to Eve or Adam. They will only have one outgoing edge. It shouldn't matter. So what she does is she has to say, oh, okay, in C2, this permutation SAT is for a true because x2 is in fact less than x3 here or something like this. And she does this by essentially saying which of these two things is less than the other. So if she wanted to say x4 is less than x3, then she would pick this vertex. You can see this vertex, I hope. Here, this vertex, which indicates x4 is less than x3. Each vertex in this grid, almost grid, will give you like one comparison is true or false. And then after this, we put edges between each clause and all the comparisons that occur in this clause. So if you look at C2 over here in the left, if it is x2 less than x3 or x1 less than x2 or x4 less than x3, then it has edges to all the three comparisons that actually say this to be true. So then you do this for C2, and then if C3 is something like this, then you put these edges and you put all of them. So, and then after this, I'm not drawing it, but I will just tell you that from each vertex in this grid, Adam can go back into the start vertex in the leftmost triangle vertex. And this is essentially the game. Now, all that remains is for me to tell you where the smiley faces and sad faces occur for it to be a Rabin game. And this is kind of simple in that each number from 1 to k, x1 to x, here I have x1 to x5, right? So each of them has a different color. So here I will assign x3 to be yellow, and everything in the row of x3 will have a smiley face of yellow. And everything in the column of x3, on the other hand, will have a sad face of yellow. If x4 was given purple, everything in the column of purple will have a sad face of purple, and everything in the row of purple will have a smiley face of purple. So this is essentially how the colors of these games go. So now that you have these colors, you can kind of, it's maybe hard to prove in the next 5 minutes, but I can intuitively convince you maybe of one direction at least. So if at all I have a satisfying assignment of this permutation set, if I have an actual permutation in mind that satisfies this, and I keep going to the right clauses that will satisfy this permutation, then let's say in this permutation, the largest, comparison that occurs is like x4 or something. So I will never, the smallest one that occurs is x4. So you will always see the purple smiley face, but never the sad purple smiley face, because there will be no clause for which E will say, oh, I'm going to something which says this is x3 is smaller than x4, because we're assuming that x4 is the smallest. So then it will be satisfied. The other direction is also not very difficult to see. And again, this takes 1 minute of staring at it, or maybe not one, but a few minutes of staring at this to convince yourself that this reduction actually works. So what this does is that you can show that our algorithm to solve Rabin games is also quite tight in that you have this 2 to the little o of k log k. If you had a 2 to the little o of k log k algorithm to solve Rabin games, then you'd be breaking the ETH, which many people believed in. And we were able to reprove this in a proof that was like barely a couple of pages and we just had 2 pretty diagrams, I would say. And what I will do is I think I will stop the talk here. And then if you have any questions or you'd like me to go over any of these in detail, I would do that. But if not, then I will stop here.
Thank you very much for the very nice talk, Thejaswini.
Thank you.
Any questions? Yes, please.
Thank you very much indeed for your talk. I always wonder about proofs like combinatorial proofs like this. The proof itself can be a topic for formal verification. Did you try to validate your proof using any proof assistant?
No, we haven't done this.
Because please understand, I have some experience of this kind. Basically, appealing to human understandability is not very sound. Try to do it.
Yeah, thank you.
Thank you. In any case, thank you indeed.
Thanks.
So I have, anyone, any questions? While people are thinking, so I have some questions. So in this lower bound, when you show, so roughly for every color, there are same number of vertices.
More even, right? Because if there are at least k square many vertices here. And there are k different colors. So we are reducing an instance of a permutation set into a Rabin game. So here there are as many colors as there are literals, as there are these xi, x1 to xk, these temporal variables, as I called them.
So
you
my
have
question is about the distribution, in the sense, like if I just look at the number of vertices, let's say there are n1 vertices which are colored with color 1, n2 with color 2, and so on.
Hmm.
Is this a parameter in sense, like if I look at, you see, like maybe my question is, if I have there are very few vertices with a certain color, there are many more vertices with a different color, let's say. If I can I
Hmm.
use this information to kind of give better algorithms?
uh Probably, but maybe not by too much, because in the NP hardness proof of Rabin games, they use only one color in a vertex once, essentially, if I'm not wrong.
I see. Okay.
So that already, I mean, maybe it can be better than k factorial, but no, still would be exponential, is my conjecture.
Okay. Another question is that so for parity games, there are certain instances which are known to have better complexity in terms of, as you know, DAG width and so on.
Hmm.
Is it are there something like that known here for Rabin games?
So our proof already excludes a lot of these width-based parameters, because this very graph that is on the slide has tree width constant and DAG width constant, because it's essentially connected by this one triangle vertex of sorts. And like if you remove this, the whole graph kind of can be disconnected. And this means that you can't parameterize Rabin games based on any of these width parameters and hope to get better algorithms. I mean, maybe not this exact graph, but I know that you can modify this graph to get a graph of smaller tree width and DAG width. So this is,
I see. So okay.
it was,
Okay.
yeah, it was one proof that killed all the future results section I had written.
Okay, very good. Okay. Thank you.
Thank you.
So, Thejaswini, yeah, thanks for a very colorful and picturesque talk. But so basically, you show a kind of an optimal space and time-wise solution for Rabin games. But does it also shed, does it give any, does it shed any light on games for other kind of games? I mean, algorithms for solving other kind of games like parity, or can you convert them into a Rabin game? And
so usually Rabin games are converted to a parity game, because parity games can be solved faster in some sense. And what we like, the techniques that we used are also based quite heavily on how parity games are solved themselves. So I wouldn't expect that the conversion from parity to Rabin would help. But like all these solvers for I mean, in SynthComp, when people try to solve these instances and they try to do this via Rabin games, most of the times they convert the Rabin game to a parity game, and this might like help bypass this construction of trying to solve the parity game after having the Rabin game converted to a parity game. And when you said other games, maybe not parity, but one line of work is to extend these kind of algorithms to solve with other objectives, like Mueller objectives or Emerson-Lee objectives would be like a good way to solve, I mean, good approach to take, because these games, at least what I think is called colored Mueller games, are p-space hard. So they are kind of harder than Rabin games, but how they are solved are also by converting them to a parity game and then solving the parity game. So like you can think of this as lifting parity game algorithms to solve Rabin games. Probably one could also lift very similarly parity game algorithms to solve Mueller games, and these kind of other games which work. The immediate obstacle is that Rabin games have a positional, and that was very important to our.
okay. So in terms of practical applications, are there places where, these games arise naturally and you would like to solve them, or?
8 o'clock, so that's good. Hello? I don't think I heard you in the last few minutes.
No, sorry. So are there kind of natural places where such games, where the Rabin conditions apply? I mean, do they arise naturally in some setting?
Yeah, so if you think of specifications like the following, Rabin and street are quite ubiquitous because street condition essentially says which street is exactly the complement of Rabin. So Eve's winning strategy was, oh, she should see the smiley face infinitely often and no sad faces. And the opposite of this was, no matter what, Adam should always see a sad face every time he sees a smiley face. And this, if you think of this, is the equivalent of saying, if I ask for a request infinitely often, then I want it to be the server to grant me this request every time, like after infinitely often as well. So you kind of, it's a direct way of encoding fairness and so on. So it's not just for LTL synthesis, but you also have these conditions arise naturally to encode several properties of fairness.
And these algorithms may not extend to infinite state games. I mean, of course, they may not be decidable, but can you say
So
that,
depends
if
on how
you're...
these infinite state games are represented. So if there is some finite abstraction of these games, then it might be able to somehow extend these games to these finite, pull it back in some sense. But as such, infinite, it depends on the very specific instance, I suppose.
Yeah, let's say logically specified games, but the states could be infinite. But like a fixed point algorithm, if it terminates on the infinite state game, you could still, you still compute the exact winning region.
Yes, but
I don't think this algorithm extends to that kind of...
yeah, so this is not exactly a fixed point algorithm it's okay, maybe it is some kind of fixed point algorithm, but it's not like a symbolic algorithm which has access to these states as such. But maybe, if I'm not wrong, I think there are some people trying to work on symbolic algorithms for these kind of games recently, and it has been, it's a paper in VSS-IARCS this year as well.
I see.
So maybe that might be more helpful. But it would be interesting to see how this works, because at the end, it's understanding how these logical representation of these games work.
Okay, thanks. Thanks, Thejaswini.
Any further questions? Okay. Yeah, if not, let us thank Thejaswini once again. Thank you so much for the talk.
Thank you for the invitation and the questions. See you.